lecture with this very nice kind of pictorial interpretation of the Gauss curvature. Huh? So just by looking at the surface, you now can guess where the curvature will be possibly positive or negative. Remember, we said thanks to the fact that the second fundamental form is the Hessian of the height function over its tangent plane, essentially, at one point. Then, if the point is elliptic, then there must be a neighbor of the surface which lies on one side of the surface. So, of course, you cannot decide whether the height function will have a maximum or a minimum, because this depends on the choice of orientation. Okay? But, you see, in fact, that's why I'm saying it's staying on one side. I don't know which one. I cannot decide which one with respect to n. It doesn't matter, but there is at least a neighbor. Of course, I cannot control, by knowing k of p positive, of course, I cannot control what the surface will do somewhere else. Okay? But at least in the neighbor of this point, it must stay on one side of the tangent space. While the dual theorem is, what does it happen for negative curvature? And the point is that a point of negative curvature will look like kind of a saddle. Okay? So there must be one direction, or at least, so in every neighbor, the surface will cut the tangent plane. It will be a bit above and a bit below. Okay? This is not an if and only if, because there is the problem of zero curvature. Okay? Because this is due to the problem in calculus that, of course, if the Hessian is semi-definite, you cannot conclude that the function has a maximum or a minimum. Okay? And that's exactly. And in fact, but on the other hand, you might say, well, but this is not just any function. Okay, we know that in calculus there is a problem. Maybe the height function is a bit special. So you might conjecture that there is actually a theorem for zero curvature. So can you characterize geometrically zero curvature just by looking at this type of properties of the surface? So this is a good excuse to write down another couple of interesting examples of surfaces, because the answer is no. So, well, remember, zero curvature appears in two ways, which are kind of geometrically distinct: planar and parabolic, meaning the whole second fundamental form vanishes, because the Gauss curvature is at the determinant. So if you think of a matrix, okay, you're saying the determinant is zero, but what does it mean? That the matrix is zero, or just the determinant? Right? It's non-zero with zero determinant, okay? So this could be okay. So, for example, of course, which surface, I mean, the source of examples of for planar points, planar means the second fundamental form is identically zero at that point, is of course the plane. Okay? So for the plane, what kind of theorem do we have? Well, actually nothing, because for the plane, the tangent plane is the plane itself. So you can say both. You can say either it lies on one side or intersects or whatever. I mean, it's kind of the undecidable. But for example, take this surface here, S to be it's actually a graph of a function. U cube minus 3v squared u. Okay, so where u and v lies in R2. Okay. In fact, since we haven't done many exercises up to now, let's do the complete exercise. Let's complete. Of course, 0, 0, 0, so the origin of R3 lies on this surface in response to the choice of u and v equal to 0. So let's pick E to be 0, 0, 0, and let's do the computation. So again, this is the moment of start computing without thinking. So this is 1, 0, 3u squared minus 3v squared, xv is 0, 1, minus 6v x UU is 0, 0, 6U, x UV 0, 0, minus 6V, x VV is equal 0, 0, minus 6. Okay? So now I need n, the normal vector. The normal vector, I get it from here. It's minus 3u squared plus 3b squared plus 6v plus 1 divided by its norm. Okay? So this has to be normalized, and I don't even write the output. Okay? Divided by its norm. It will be a function, the square root of 1 plus 36v squared plus this mess squared. Okay? It's possible I'm doing mistakes. Huh? I mean, so.
X of V is the 0, 1, minus x of
The
V.
last one.
Last one.
Yeah, I think.
Yeah.
It's
X of V, X of V.
6b minus
Yeah.
6b.
The mistakes from X of V. X of V is 0, 1, minus
Because
6
there
of
is
V.
6 UV.
Oh, 6 UV, you're right.
And so
And this will become 6U.
B.
And then,
6b. U, sorry. Yes.
and then everything else is fine.
yeah.
Okay, so this was an error here, so this will be an error here. 0, where this disappeared, 6 minus 6 UV. Okay? Okay, very good. So, and now let's compute the coefficients of, well, I don't compute the coefficients of the first fundamental form. At the moment, I don't care because we are speaking about planar, non-planar, and so on. So let's compute directly the coefficients of the second fundamental form. So this will be n xuu, n xuv, and xvv. Okay, so n xuu is 0, 0, 6u. Okay, little f is minus 6v, little g is minus 6u. Okay, now I should do k at the point. Of course, if I want to write the general formula for k, I also need the capital letters, but I want k of p, and if you look at what I wrote, it's enough what I wrote, because it's eg minus f squared divided by eg minus f squared. The point is whatever there is at the denominator, p is the point corresponding to 0, 0. So p is x of 0, 0. So I need to put u equal to 0 and v equal to 0 here, and everything vanishes. Okay? So this is 0. So, okay. And in fact, okay, the Gauss curvature is 0, but actually it is 0 because the second fundamental form disappears completely. At this point, the second fundamental form is 0, 0, 0. Okay, it's not just the determinant. Okay? So it's a planar point. So P is planar. Okay, so now I'm curious. How does it look like, the surface, in terms of this kind of geometric interpretation? Okay, you take your computer and you ask it, or let's see, I should have practiced a little bit. It looks like this. Well, even without practicing, it was not that bad. This is S. Okay? But it's a graph of this function, no? So now the question is, and 0, I mean the origin is actually part of this surface. Okay. Now this is a famous surface for various reasons, and Courant gave it a name, Hilbert actually gave it a name, just to remember. Okay. It's the monkey saddle, because of course you have space for two legs and the thigh. So if the question is, well, now I pick the tangent space, well, actually, what is the tangent space at the origin? The tangent space at the origin, again, I need to take, it's the vector space generated by these two vectors. At this point, I need to put u and v equal to 0. So this disappears. So what is left? Is left the horizontal plane. Okay, the standard R2. So it's z equal to 0 inside R3. So actually, the tangent plane at this point is exactly the horizontal plane. Okay. And now, does the surface lie on one side? No. Okay? Clearly not. It's actually quite obvious if you start playing with cubic equations, of course. A cubic will be somewhere negative and somewhere positive, okay, near 0. Very good. So this is an example of a planar point where the surface actually seems to behave. I mean, on the other hand, if I had given to you this picture, you could have said, well, it was right to think of P as a candidate for negative curvature. So this has exactly the same behavior of a point, of an hyperbolic point. No? Because this is what's happening for hyperbolic points. It's crossing. Okay, so for planar points, we cannot conclude anything. But I don't want to spend the whole lecture on this issue, because now you understood how to play and construct counterexamples to any conjecture. Let me just tell you, for example, what are the zero curvature examples that you have that you can put all together. So you have, for example, now you have this example for planar. You have the cylinder for parabolic. But of course the cylinder behaves, and the cylinder seems to behave like what? Well, if I pick a point and I draw the tangent plane, the cylinder lies on one side. So these are parabolic points, and they seem to behave like elliptic points. Okay? So that's another source of examples, and then you can draw pictures like this. If you take, so now I'm describing to you another, you can take a curve like this. Now imagine you can actually write down, so imagine that this is a function f of x, I mean z actually. Well, it's a cubic equation, but suppose you can actually write, so this would be the z-axis, and this would be the y-axis, okay? So now up to you to find a function which has this graph, a graph like this, okay? Take this surface like this and rotate it around the y-axis. Sorry, take a curve like this and rotate it around the y-axis, okay? So you are really thinking of a surface now which really looks like this, okay? I should draw the symmetric curve, okay, on the other side, and then very good. Now the point where things could be interesting here, if this curve is sufficiently high degree, in this 3, then actually you can prove that this will become a parabolic point. Okay? So that's another type of surfaces where k is equal to 0, and you can put into your conjectures about this. Anyway, the moral of all this is that for zero curvature, no theorem holds. Okay? All possible counterexamples appear. Okay. Now, before moving from this story about the second fundamental form being the Hessian of something, well, remember when we described the differential of a map from a surface to something, the two key examples were the height function and the distance, or the distance squared. Okay, so the height function, you see how much geometry has produced by looking at its Hessian. So let's see if the distance squared measures something interesting again. So let's compute the Hessian of the distance square. Now, okay. So remember, what is the situation? We have a surface S, we have a point, and now let me draw it a bit, P naught, and we are taking the function f of P from S to R to be P minus P naught squared. Okay? We already know what it means. Remember, to compute the Hessian, you need to have a critical point, but we have already characterized critical points of these functions. So we remember that we had observed that P is critical for F if and only if, and now again you have many equivalent formulations. P naught, one way was P naught lies on the normal line to S at P. Okay? Meaning, pictorially, I know, for example, well, again, when you do this, it's better to draw S as different as possible from a sphere, otherwise everything. So suppose you are taking really a surface which is very. Now, I take this surface S, so where could be? So, for example, I know that this point will never be, for sure, is not a critical point for the distance square, because you imagine the tangent space, so you imagine the normal line, and clearly this has nothing to do with the point P naught. Okay? So, presumably there will be probably something here interesting. There could be in my picture, and maybe there is also something here interesting in my picture. Okay? Just to give you a little bit of feeling. Of course, these are just pictures. So, in particular, let's write something mathematical out of this. So, what does it mean P naught lies on the normal line? That I can actually write P naught, now as a linear combination of vectors, as P plus lambda n of P for some lambda in I. Okay? This is just a mathematical rephrasing of this. So I know this. I know that P is related to P naught in this way. And now I want to compute the Hessian at this point. So D2, the Hessian of F at the point P applied to a vector V, now is what? Okay, it's the second derivative of F composed alpha. So I go and see what is F, and P becomes alpha of T. Now, instead of writing like this, I write it as the scalar product with itself, because I prefer to see it. Okay. So, of course, the first derivative, which is actually the one which will give me this equation for critical points, will be what? So this is, in fact, now I start using a shorter notation. This is the scalar product. It's alpha prime scalar alpha minus P naught twice, okay, because everything is symmetric. This is the first derivative. So the second derivative, I hope I wrote an equality equal to this at t equal to 0. Okay, but how much is this? Well, so this will be a 2 times what? Alpha double prime, no? Times. So this will be a combination. Now it's generally a combination of two things. So this is alpha double prime at 0. Now I can start putting 0 into the game. Times alpha of 0, alpha of 0 is P. So scalar P minus P naught. Plus alpha prime at 0, but it's V, okay, plus the norm of V squared, okay. But now I can take P minus P naught. I have something which tells me what it is. Okay, I can use the critical point equation. So P minus P naught is minus lambda n. Okay, so let me rewrite this as twice times V squared. Well, in fact, let me write everything. Twice V squared minus twice lambda n. Sorry, n times the second derivative. N of P, second derivative at zero, the acceleration of the curve. Okay? So in fact, don't be, now this is a moment of panic. You say, well, come on, what is alpha double prime? Because, I mean, the only thing involved here seems to be P and V, but that's exactly what appears in the proof, no, of the fact that it's well defined. And what is, the point is that this is not well defined, but this is. Okay? I mean, this formula would seem to depend on alpha. That's what I'm saying, no? But this is equal to 2V squared minus lambda, and that object here is exactly as we used in the proof of the fact that it was well defined. This is exactly the second fundamental form, in fact, with the plus, no? No, with the minus at P of V. Okay? You agree? Because that's the normal curvature. It's Euler's theorem if you want. No? Two lambda. Okay. So that's the normal curvature of alpha, which is, as we know, as we proved, the second fundamental form applied to the tangent vector. Very good. I stop here, but this is a homework for you. Out of this, there are many interesting corollaries out of these computations, again passing through the calculus theorem, okay? So, corollaries. One, there does not exist compact. I mean, these are in some sense all reformulations of the same corollary, yeah? But I mean, a compact surface with only hyperbolic points. So if you give me a compact surface, not every point can be hyperbolic. Okay? And in fact, second corollary, if S, in some sense, it's essentially a reformulation, if S is compact, well, it's a bit more than that, it's slightly more. If S is compact, there exists P in S elliptic. So in fact, more than that. If it's compact, it must have at least one elliptic point. Then, of course, if it has one elliptic point, remember that the Gauss curvature is a continuous function. If it's positive at a point, it's positive in a neighborhood. So this is not about one point. Okay? These are exercises for you. This is, of course, the key computation. Plus, let me give you a hint, which is the critical hint. And why there is this compactness assumption? Well, the compactness assumption is that on a general surface, you don't know whether there are critical points for this function. So this is topology at work. I put the compactness assumption just to be sure that a continuous function, well, in fact, a differentiable function, has at least two critical points, a minimum and a maximum. Okay? And now, Now I told you essentially the proof. You have just to make it work. Pick these points and compute the Gauss curvature at these points using this. Okay? You see that now it's a calculus problem, because now from here you extract the second fundamental form. And now at the minimum point you know something about the Hessian of this function, because it's a minimum. Okay? At the maximum point you know something about the Hessian of this function. You have to deduce the corresponding thing for the second fundamental form and see what happens. Okay? But these are very striking results. Okay? They are very beautiful results. I mean, they're cheap, they're very simple now, but it's already quite surprising. Okay? So, and actually, the first corollary is very important also historically, yeah, in the mathematical history. I mean, eventually we will start speaking about hyperbolic geometry, and corollary 1 says that hyperbolic geometry is not inside R3. Okay? Hyperbolic geometry means live in a universe where curvature is negative everywhere. Okay? So, if you restrict yourself to surfaces in R3, you eventually have to do at least somewhere a little bit of elliptic geometry. Okay? So that's very important for the development of the philosophy of modern geometry. Okay. Very good. Now, before moving away from this story, final but longer and nice application again of the Hessian of functions. I would like to give you, I would say, what I would call the first modern theorem in differential geometry. The first real theorem that we see in this course. This is called Liberman's theorem. Characterizes surface with constant curvature, but the point is that Liberman's proved it. In fact, nobody knows how, because nobody some way much more complicated, and Hilbert came and gave a much more elegant and simple proof of this theorem, and so now we all study Hilbert's proof of Liberman's theorem. Okay? So, and in fact, just to give also a little bit of credit to this piece of history, the first theorem, which is not actually the beautiful theorem, but it's called theorem just because it's the key lemma, and it's called first Hilbert's theorem in this story, says the following. Now this is a moment where you really have to believe that this is important, because I have to admit that this statement looks very strange. Okay, so pick S oriented. Okay, oriented means orientable with a choice of orientation n. Okay, with of course usual notations K1, K2, principal curvatures, assume P in S is such that, so assume that there exists a point on the surface which satisfies the following three conditions. 1, K of P is positive. So it's, suppose you find first an elliptic point, okay? For example, the last corollary we wrote says, for example, if the surface is compact, there is such a point, okay? But I start assuming something a bit, so K1 of P, so the small principal curvature, I also assume, so in fact K1, in fact instead K1 has a local minimum at P. Okay. And the big one, K2, has a local maximum at conclusion is that then P is umbilical. Remember, umbilical just means K1 at P is equal K2 at P. Now, I find it very counterintuitive. Okay, this is one of the moments everybody has. We will see why it's not, but at least if you see the statement, because at the end the conclusion is that actually these two curvatures are the same. And you seem to be asking that they are as far as possible. No, because so you have these two functions, one K2 and one K1. And you know that K1 is smaller than K2 by definition. And you're basically asking that K1 has a minimum and K2 has a maximum. So they seem to be as far as possible, and then the conclusion is they are the same. Okay. So, a bit surprising. Let's see why this is true. I will convince you later why this is a beautiful fact, but for the moment, believe me. Now, we first have to set up a long notation to prove it. We are assuming this point exists. So up to translations and rotations, which won't change anything in our type of geometry, assume I can put the point in the origin, for example, just for computational convenience. Assume P is equal 0, 0, 0. But not just that. So this is achieved by a translation. Now I want to use rotations in order to put the tangent space at the point P horizontal. Okay? And so and TPS is the span of 1, 0, 0, which I will call E1. Actually, I already called sometimes in the past, but now let me repeat it for clarity. It's E1, 1, 0, 0, and 0, 1, 0. And this way, of course, I will call it E2. I choose also it's oriented, so there is a choice somewhere of orientation, N. I decided, which I can always achieve by the normal vector at this point points up. This is again assumed. And also, now, this is achieved by kind of a rotation in R3, but I still have some degrees of freedom. I can rotate in the horizontal plane. Now, once I put the horizontal plane horizontal, sorry, the tangent plane horizontal, I can still rotate in this plane, fixing the axis, and they would still work. So I still have this degree of freedom. What can I do with that? Well, why not? I know that the surface will have two special directions. Inside the tangent plane, there are always two orthogonal special directions, the principal directions, no? So why not? I use this degree of freedom to decide that these two are actually the principal directions at this point. So, and E1, E2, of course, with the obvious notation. E1 will be the principal direction corresponding to K1, and E2 is the principal direction corresponding to K2. These are eigenvectors, and those are the eigenvalues, okay? Are the principal directions. Okay, so let me just corresponding to K1 and corresponding to K2. Good. So now I think I've used all the rigid motions of R3. I've put my surface in a kind of a canonical position. Now I cannot do anything else. The other thing I know is that locally, what I mean by locally near P, the surface Notice that, of course, the theorem is local. So everything, all the assumptions and the conclusions depend only on the surface near the point P. So no problem in working locally. Locally near P, I can think of S. S is the graph of a function f. Okay? Where this function will be defined on a small neighbor U of R2, which again, up to renormalization, I can decide that f, so that 0, 0, the origin of R2 lies in U, and actually f of 0, 0 is actually P. Okay? I don't have space to draw also a picture, but I'm doing nothing essentially. I just write, if I write the surface on a small neighborhood of this point as a graph, no harm in assuming that the origin of the domain is going to the point P. I mean, okay, up to.
F of 0, 0 is 0.
Sorry?
F of 0, 0 is
Sorry, f of 0, 0 is equal to 0. Okay, so that. So in fact, we have used already many times, once you have this, you have a canonical chart. I'm thinking of this as a canonical chart that I will call X. X of UV to be equal to UV F of UV. Okay, so this will be the canonical chart that I will use around the point P. And now let's translate all these assumptions in terms of the function f. I've put many geometrical conditions. I played around with geometry. Let's see how these things translate into f. Well, one I said already. No, the point that I'm putting the point P in the origin. What does it mean that the tangent plane is spanned by these vectors? Again, no harm in assuming that. So this condition here translates into what? In the fact that if I take the partial derivative with respect to u, so remember, what is xu? So here I wrote it like this, but on the other hand, now I have a chart, so TPS is also the span of xu, xv. So what does it mean that these two things are the same? Again, up to a rotation, I can assume what? That actually xu is this one and xv is this one. So xu is what? It's 1, 0 fu. So what does it mean? That it's 1, 0, 0, that the partial derivative at this point, only at this point, is equal to 0. And the same for fv. By this symbol I mean the partial derivative, of course. Huh? Okay, so this translates into the fact that xu has become the vector, so this means i.e. xu is equal to e1, xv is equal to e2. At the point P, only at this point. Well. On the other hand, I don't even remember, have we done the general computation for the second fundamental form of a graph? In general. Very bad. My mistake, so now we stop the proof, because now I'm going to write the coefficients of the second fundamental form in terms of the function f. But this is completely general. In fact, let me do it as part of the proof, but you can isolate it and it's kind of an exercise on a side. Every time your surface is the graph of a function, let's do the standard xu, xv, xuu, xuv, xvv stuff. No? I mean, let's do the exercise in general. So this is 1, 0 fu. This is 0, 1 fv. This is 0, 0 fuu. This is 0, 0 fuv. And this is 0, 0 fvv. Okay? Plus n. N, of course, will be what? Minus fu. Minus fv, 1, divided by its norm. okay? Well, actually, in this case, maybe the norm it's worth writing. It's 1 plus fu squared plus fv squared, 1/2, okay? Very good. So how much is E? Well, E is n xuu. So it's 0, 0 fuu divided by 1 plus fu squared. In fact, let me write it here because I will use it, then I can erase. This is a quick exercise. So E is equal to fuu divided by 1 plus fu squared plus fv squared, 1/2. Okay? What is little f? Well, now it's all the same, of course. We just have, oh, of course, no clash in notation. This little f is not the function f. It's the coefficient of the second fundamental form of the diagonal. So it's fuv 1 plus fu squared plus fv squared, 1/2. And little g is fvv divided by 1 plus fu squared plus fv squared, 1/2. Okay, so I can erase this quick computation. Oops. This I fb 0, 0 equal to 0. Okay. Okay, so that's what we know. Very good. But remember, so I've used almost everything. I mean, I translated almost everything in terms of the function f, except this one. No? So what does it mean that these two vectors are actually the principal directions? Well, in particular, it means that at this point, the second fundamental form is diagonalized by these coordinates. Okay? So this thing, how do I phrase this condition in terms of f? This is equivalent to what? I decided that the uv coordinates are actually giving me the eigenvectors. So if I write the second fundamental form in these coordinates, I must get the diagonal matrix. Okay? Do you agree? Do you agree with me? Very good. But on the other hand, the matrix is this one. So it has to be diagonal. So in particular, this is 0 at this point. And these are only at the point P, because of course diagonalizing at one point can be completely different from any other point. But in particular, now I know that f of u at the points 0, 0 is equal to 0. Plus, well, now it's just a matter of, now this is off the diagonal. And on the diagonal, I must have the eigenvalues, of course. But this is just fuu at 0 is, at 0, 0 is k1 at p, and fvv at 0, 0 is k2 at p. Okay? Up to now, I've done nothing. I've just rotated and translated my surface, and I've put into a canonical position. I wrote it as a graph, and I translated all these things into conditions on the functions, which is giving me the surface. Okay? And the blackboard is incredibly small. So I need to keep them. Remember the three assumptions, okay? Elliptic, minimum for the small, maximum for the big. I mean, that's the way I remember, okay? So now I know all this stuff about my function f. In fact, now I can even erase it. Well, no, this I will use them later too. Because sooner or later I will have to move away from this point. So I still need to know all this formula for the nearby points. So, okay, so now let's start doing something. Now define two curves. Alpha of u, now this looks like a big strange definition, let me comment on this. So be x of u, well, it's not really strange in the sense, what is this? I'm taking, imagine I cannot draw too many pictures, so in R2, in the domain u, I take the x-axis, the u-axis, and I go and see how it looks on my surface, and I call it alpha, okay? And of course I will define beta to be the other thing. Okay, so these are kind of the image of the two axes, but now on the surface. But along these curves, I want to define these two vector fields that I will call E1. Okay, E2 will be a function of u, and E1 will be a function of v. So this will be the derivative of x with respect to v at the point u0 divided by its norm. So this is just normalized. And E1, this time is a function of u, is kind of the dual, is the derivative xu at the point 0v divided by its norm. Okay. Now, okay, these are, if you want, these are again curves in R3. Now, for every point, I get a vector, no? But what kind of, in fact, I want to think of them as vector fields. But vector fields along what? So the point is that if you notice E1, sorry, E1 of V. E1 of V lies where? Well, it's not just any vector. Up to renormalization, but this is a tangent vector to the surface because it's of the form xu. Okay, so it's a tangent vector to the surface, so it's not just any vector in R3. At which point? So this lies in the tangent space to S at the point corresponding to this point here. No? At the point x of 0v. But now I gave it a name. What is the point x of 0v? It's beta of v. And where is E2u? Again, it's a tangent vector because it's of the form x derivative. Now this is at the point u0, but x of u0 is alpha, so this is at the point alpha of u. Okay? So you have to imagine that you have these two curves on the surface. At every point on each of them, I have a direction, one each. Okay? So, basically, I go and look how the second fundamental form changes along these curves in these directions. That's the idea. I just want to make this computation. I'm curious. I cannot convince you why it's a good idea. I mean, of course, eventually, that's what we are studying, second fundamental forms. But why this? I think only at the end you understand why this was a very smart idea. So let me define a function, h1 of v, to be the second fundamental form at the point beta of v. So just try to be consistent with these 1 and 2. So h1 will be kind of the second fundamental form in the direction e1, okay? But if I want to do in the direction e1, I am at the point beta of v. So the second fundamental form at the point v, beta of v, apply to the vectors e1v, e1v. Okay? I will write it down what it is in a moment. So just to gain a little bit of space, I write it here. And what is, of course, h2 of u this time will be the second fundamental form at the point alpha of u applied to the vectors e to u, e to u. Okay. But how much? I mean, now, in fact, I want to express this function in terms of f, the function which is giving me the surface as a graph. And I have all the ingredients, because I know the coefficients of the second fundamental form. And remember that these are true everywhere in the local chart. Okay, not just at the point P, that's why I didn't erase. At the point P, I draw some conclusions. But these formulae are true everywhere on U, on X of U. Okay, so, and E1, actually, for example, let's focus on E1. E1 is essentially up to renormalization, which I take out because it's a quadratic form, so I know how to do it. It's XU, so it's the first direction. No? In my choice of basis, I've chosen XU is the first vector of my basis. And this, again, is true everywhere, locally. So, this I'm trying just to convince you, I mean, who tells me what is H1 in this language? Apart from the renormalization, we will discuss it in a moment. If E1 was just XU, sorry, yeah, XU at the point 0, so forget for a moment the fact that we are renormalizing it. That's by definition, so XU is the first vector of the basis. So what does it mean that these are the coefficients of the second fundamental form? What is E? Not this formula. What is E by general theorem? Is the linear operator, whatever that is, the quadratic form, the linear applied to the first vector and the first vector again. So that's exactly that one. So this is E. Okay? But instead of writing E, I write the formula for E. So this is FUU divided by 1 plus FU squared plus FV squared. And now I still, but there is this. Okay? Of course, this is a quadratic form, so this goes out. Now imagine that you are doing second fundamental form. So I replace this with this. And here what I wrote is XU. And this is divided by 1 over the norm square of XU. But now think for a moment, what is the norm square of XU? In terms of forms, coefficients, blah, blah, blah. It's the first coefficient of the first fundamental form. So here I should write capital E. But again, I don't want to write capital E. I want to write its expression in terms of this function which is giving me a graph. Are you with me? And I erased it because, of course, I'm very smart. So I have to do it by heart without doing it. How much is capital E? Is 10 FU. No, XU is 10 FU. How much is its norm squared? Well, it's 1 plus FU squared. Okay. Okay. Now, same for the second one. This is the second vector, so this will be little g. Little g renormalized. Okay. Okay, so this is FVV divided by 1 plus FU squared plus FV squared, and now the renormalization will give me G, the capital G. But capital G, again, I have to do it. It's 1 plus FV squared. Now the point is that these objects, where are they computed? Actually, I should have finished. These are computed at the point V or at the point beta of V, which is the point X of 0V, because these are functions of two variables, so I really have to be a bit careful where. Okay, and this is, of course, the analog, it's at U0. Okay, very good. Okay, so this was the setup. Now let's start notice that this is true always. I mean, I haven't used anything. This is any surface around any point, blah, blah. So now let's start putting into the picture what we know. We have three hypotheses, not one, three. So let's see. How much is H2 at the point 0? At the point 0 is the second fundamental form at the point P. No? Apply to the vectors E2U, actually at the point 0, this becomes what? E2, the little E2 of before. No? Okay, so this is second fundamental form at the point P applied to E2, E2. This I just substitute what they are. But because of all my assumptions, this is what? This is K2 at the point P. I know that this is the eigenvalue at the point P because of my choices of rotations and so on. Okay? But now, I'm assuming what? That K2, the big one, has a maximum. So P is a local maximum. But for sure, for sufficiently small u, I can certainly say that this is greater than or equal to K2 at the point x of, which one do I want? U0, or, well, let me use all these notations since I have it, alpha of u. It's the same thing, of course, but it's just written in this form, okay? But K2 at the point alpha of u, okay, this is the biggest eigenvalue of a quadratic form. So this is a linear algebra, I'm not using it. What is it? I'm claiming that this is greater than or equal, I continue here, with the second fundamental form at the point alpha of u applied to the vector E2 of u, E2 of u. Now, this is linear algebra. Do you agree with this? No. Well, you have to. This is not democracy. But think for a moment. I mean, this is it's a beautiful characterization of eigenvalues, if you want. I mean, so the biggest eigenvalue of something is the maximal value that this function can have on the set of vectors of a given norm, of course, because if you just rescale, there is no maximum value, okay? I mean, I'm sure you have used it already many times. I mean, when you take, this is something you apply, it's a principle that you apply very, very often, for example, even in functional analysis, for example. It's everywhere, okay? The biggest eigenvalue dominates the whole map. This is like saying whatever, because I don't know whether this is an eigenvector at the point u. The important thing is that you understand what is the problem. These are vectors in the tangent space at alpha of u. At alpha of u, I don't know which are the principal directions. I could fix them at the point 0, but I cannot say anything nearby. Okay, so really I know nothing about this. But I can say that this has to be less than or equal than the biggest eigenvalue. And this is just because this has norm 1. Otherwise, I should say the biggest eigenvalue times the norm squared of the vector. Okay, this is a linear algebra exercise. I'm not going to, because actually it takes a line to prove it. Okay, so, but are you convinced that this is plausible? I mean, otherwise, why do you call it the biggest eigen? I mean, in some sense, you have to imagine that if you have something which has eigenvalue 1, 2, and 3, and you want to measure the norm of the action of the vector that you obtain by acting with this thing. Well, if you put 3, that's the biggest you can get. Okay? That's, I mean, it's not a particularly subtle thing. Okay, but given that this is actually in my language, this is what? This is h of u, h2 of u. Now by definition, this is h2 of u. Okay? And here, what did I use here? The fact that the big one has a maximum. Now let's do the dual thing with h1. So h1 at 0 is the second fundamental form at the point P of E1, E1. And this, by our construction, is K1 at the point P. And now this has a local minimum. So now I say that this is less than or equal to K1 at beta of V for any V sufficiently small. Very good. But this, again, same principle twisted. I mean, dual principle. This is the smallest eigenvalue, so this is less than or equal to the operator applied to anything. So, to the second fundamental form at the same point, of course, beta of V applied to E1, E1. Which, in our language, is now H1 of V. Okay, so these are the translations of two hypotheses. So these two functions. So what have I discovered? The function H2 has a local maximum. I mean, so the translations of the principal curvature assumption on K2 tells me H2 has a local maximum at 0, and H1 has a local minimum at 0. Because this, of course, this holds for any V on these curves at least. Okay. Yeah, but these are functions of one. But then, actually, this was by brute force comparison, but what I said is that, let me translate what I said, H0 as a local maximum, okay. So I know something about H double prime 2 at the point 0, not everywhere, but at least at the point 0, and since this has a maximum, this has to be less than or equal to 0, okay. And H double prime 1 at 0 is greater than or equal to 0. Okay? Very good. Now, okay. Now I hope you believe me, because otherwise it takes half an hour. What do you do? So we translated our hypothesis into these two things. But notice that I've never used this. And now you really have to be brave. Okay? Because H1, H2 is equal to this as a function of u. Write down the second derivative. Okay. Be free. You have to know that you have 15 minutes free. Okay? Ah, that was bad. Because actually this I need. Let me do it only for H2. Okay, so I erase H1. The other one, let's do it. Let's try to do it quickly. So let me phrase this condition now in terms of this expression here. I mean, they are the same. I mean, I have this expression, so I need to. So, of course, if I want to compute the second derivative as 0, the first thing I have to do is to take the first derivative, but at any point. I mean, I'm not allowed to put u equal to 0 in the first derivative, because I will have to take another one. Okay? Okay. And actually, trying, but just trying, to minimize the mistakes, let's write this in terms of a product of powers, okay? Because I get confused by, so this is actually FVV times 1 plus FV to the minus 2 times 1 plus FU squared plus FV squared to the minus 1. I mean, that's at least my way to minimize mistakes.
I think this is a mistake.
Square
The second factor.
It's minus.
And it's true, there is no square. It's the norm squared of that vector, so no, it's minus 1. Okay,
FB is there.
Sorry?
Plus FB.
Oh, but there is a square here, yes. Okay? Good. I mean, at least that's the way I think I can minimize my errors, and in fact I should have written in this way because I will start with the first one. Okay? So now I take the derivative of this times this, plus, and so on. Okay, so this becomes what? Minus 1 minus 1 plus fv squared minus 2 times the derivative of this with respect to u. So this becomes 2 fv fuv. Okay? Times everything else. Times fvv 1 plus fu squared plus fv squared to the minus 1, and I've done only this one. Okay? Plus, now I don't touch the first one, 1 plus fv squared to the minus 1, and then I do the same thing, but then of course the plus becomes a minus, minus 1 plus fu squared plus fv squared to the minus 2 times the derivative of this thing, which of course becomes twice, minus twice, I put the 2 here, fuu, this is a function of u, okay? So twice, I put the 2 there, so it's fuu plus fuv. Times this one, okay? Plus, first one I don't touch, second I don't touch, and now this with respect to u, sorry, fuv, okay? All this eventually computed at the point u0.
Second term is.
This one here is a mistake.
Yeah, third term.
This one,
2fu times fuu plus 2fv times fv.
you're right. 2fu. Well, the 2 I put it here. So let me gain a little bit of space here. It's fuu plus fv fuv. Okay, now we agree? Okay. Now you see why you have to be brave with 15 minutes free, because this is still the first derivative. Now you have to take the second derivative. But this actually, it's a moment that if we slept enough, you realize by looking that actually you don't have to take many derivatives. Because now at the second derivative, you know that you are going to compute it at 0. And that's why I haven't raised this blackboard here. Because now, every time, I mean, now do it by fantasy, no? I mean, now I have this expression, I start taking derivatives. And then I start computing it. So, you see, for example, in fact, let me write immediately what is, in fact, I was joking a little bit, of course, because it's not, this was harder than the second. I mean, the second, because, for example, if I take, do I have to take the derivative of this? No, I would be completely stupid, because I know that there is this one. Okay, so in fact, what do I have to take derivative of here in order to gain something non-zero? Well, in principle, the only thing that could survive is when I take the derivative of this. Because every time I take the derivative of something else, this will kill the output. Okay? Do you agree? So let's write down, so out of this mess, the only thing which survives is this one. And actually I can even start putting what is left at the point 0, because I also know that fvu is 0, fv is 0, so on. So So this becomes minus 1 times 2. Okay, so it's actually minus 2. Oh, sorry, there is also this one. Okay, so actually there's no way. I mean, here, either this or this will kill everything. Okay? Very good. So the first line, it's actually disappeared immediately. The second line, well, something should remain somewhere. Well, if I take the derivative of this, whatever I get, it will be multiplied by FV. But FV we just discovered, no? Because remember, whatever I do, at the end there will be a 2FV, no? So this I don't have to differentiate. This is disappear. Well, yes, because again, there is here, I mean, this term is 0. So if I don't touch this term, everything will die. So I have to touch it, and how? FUV, I'm taking the derivative with respect to u. So if I take the derivative of this, nothing will change. It will be 0 anyway. So I need to take the derivative of this with respect to u, and actually something here survives finally, because the derivative of this, so in fact, okay, now let's write down what is left. Minus 2 times 1 times another 1 times FUU squared times FVV. And that's it. That's the only thing. Okay?
No, plus.
Is another term?
The FUU supposed to differentiate. Okay, that's close to 0.
What else?
Yeah, no, it's okay.
Okay.
Fine.
The second line, it's only this. Of course, this meant evaluated at 0. When I go here, this I know now, I don't have to touch it. This I know I don't have to touch it. I can touch this one, and I have no idea what are the third and fourth derivatives, so this has to be there. So this is plus 1, 1, F, U, U, V. Okay? Very good. So all this, of course, is evaluated as. Okay?
F is the
Modulo at 2. There shouldn't have been at 2, but I mean, let's see. Now, I don't do it, but you play the same game for H1, and I tell you, hopefully, the result. So what is, on the other hand, H1 double prime? With the analog formula, no? You take the same formula, you play the same game. So H1 double prime at 0 is equal to what? Becomes minus FVV squared. It's actually the dual, of course. It's the same formula switching FUU plus, but actually there seems to be not this 2 here, which is a bit annoying because now it will take us 10 minutes to decide why it was not there. So, okay, but in any case, this has to be right. FUU VV at 0. Okay, so now let me think for a moment where these 2 came from. Of course, these 2 came from there. So why there was this 2 here? Because this I erased the formula, of course, so this was the derivative of FU. When I took the derivative of this, I was taking the derivative of this term here. And I said this is twice, because actually the truth was that this 2 was here, no? It's 2 FU FUU plus 2 FV FUV. So I put the 2 there. So how come now this has disappeared? pretty sure if we do the same computation here, eventually if we do it our way, here we would get a 2. So what do we know? That H2 at 0 is less than or equal. So now the equation we have, the inequality we have is that this is less than or equal to this. So if we repeat the same thing here, we would get a 2. And now would this be enough to prove anything? Yeah, I think it's okay. Look. Okay, of course, my proofs are modulo double checking, okay? But let's see if this eventually converges to something. So, of course, the inequality we have is that H double prime 2 at 0 is less than or equal to H1 double prime at 0, okay? So what does it mean? You see, of course, if I write down both, now I see that there is a term which is equal, okay? So in fact, what we got here in terms of F is that at minus 2 FUU squared FVV is less than or equal to minus 2 FVV squared FUU, which I think, so this 2, you see, I think it's irrelevant. Okay, so in particular means what? Of course, I can write this however I want. I prefer to write it on this side, so this I write it as FUU FVV. Okay, I take this on the left, and here I'm left with FVV minus FUU. And this is less than or equal to 0. Okay? So you see that 2 was actually not important. But what are these? So these are every time now, from now on, of course, I'm evaluating at u equal to 0. Okay? So this at u equal to 0. Geometrically, what it is? Okay. Because now we go back at the point P, but at the point P, we know what these objects are. So you replace these things, so you get what? K1, K2 times K2 minus K1. So this is the same thing, because it's evaluated at the point P of the Gauss curvature times K2 minus K1, or vice versa, K2 minus K1, no, that's the one I like, at the point P less than or equal to 0. And now you see it's done. It's game over. Because which is the third assumption. We have already used minimum of the small, maximum of the big. We still haven't used anything about the Gauss curvature, but that was the first. If K of P is positive, this implies what? That I can erase this. Okay, but then K2 is less than or equal to K1. But K2 is supposed to be the bigger one. So how is it possible? The only solution is that K2 is equal to K1. Okay? So it's umbilical. Okay, it's a small tour de force in derivatives, so that's a nice idea. Okay, then it took me longer than expected, so corollaries next time. I leave you with a little bit of suspense, because I have to confess, as it is, it doesn't look like a great theorem. I mean, who cares? I mean, there are so many hypotheses. I mean, so the point has to be elliptic, and then in the same point there has to be these two miracles, no? K2 has to have a maximum, and K1 has to be a minimum. And actually, the conclusion is also that the point is umbilical, which of course is interesting, but it's not such. I mean, it's not the end of the world. So both, if you analyze critically the hypothesis and the thesis, it looks like Hilbert could have gone to play football that day. And, okay. But actually, the corollaries will explain why. Fortunately, he didn't go. Okay. Okay, so see you next time.